Protostar. A protostar is the earliest stage in a star's life. It forms when a massive cloud of gas and dust begins collapsing under its own gravity. As the cloud shrinks, the center becomes hotter and denser, creating a glowing ball called a protostar. Unlike a true star, a protostar hasn't started hydrogen fusion yet, so it isn't powered by nuclear reactions. Instead, it shines because gravity is squeezing it tighter and tighter. This stage typically lasts from 100,000 to a few million years. Once the core reaches about 10 million Kelvin, hydrogen fusion ignites, and the protostar officially becomes a real star. Every star in the universe, including our Sun, began its life as a protostar. Tauri Star. A Tauri Star is a very young star that's almost ready to begin its life on the main sequence. It forms right after the protostar stage, when hydrogen fusion has either just begun or is about to begin. These stars are less than 10 million years old and are surrounded by thick disks of gas and dust, the same material that can eventually form planets, asteroids, and comets. Tauri stars are highly active, producing powerful solar flares, strong stellar winds, and unpredictable changes in brightness. Because of this, they can appear to flicker over time. Our Sun likely spent a few million years as a Tauri star before settling into the stable yellow dwarf we see today. Brown dwarf star. A brown dwarf is often called a failed star because it formed like a star but never became one. It contains too little mass, between about 13 and 80 times the mass of Jupiter, to sustain hydrogen fusion in its core. Unlike true stars, brown dwarfs never shine brightly. Some can briefly fuse deuterium or lithium, but not ordinary hydrogen, so they gradually cool and fade over billions of years.
Have a great time.
Their surface temperatures range from about 300 to 2,500 Kelvin, making some brown dwarfs cooler than certain planets. Although they're extremely faint and difficult to detect, astronomers believe brown dwarfs may be almost as common as normal stars. Red dwarf star. A red dwarf is the smallest and most common type of true star in the universe, making up nearly 75% of all stars. They have surface temperatures between 2,500 and 3,500 Kelvin and contain only about 8% to 50% of the Sun's mass. Despite being much cooler and dimmer than our Sun, red dwarfs are incredibly efficient. They burn their hydrogen fuel so slowly that they can survive for hundreds of billions to over a trillion years, far longer than any other type of star. In fact, the universe is only about 13.8 billion years old, which means not a single red dwarf has ever reached the end of its life. Every red dwarf that has ever formed is still shining today. Many of the stars closest to Earth, including Proxima Centauri, are red dwarfs. Because they are so common and can live for trillions of years, scientists believe they may be among the best places to search for planets, and perhaps even extraterrestrial life. Orange dwarf star. Orange dwarfs, also known as K-type main sequence stars, are the middle ground between small red dwarfs and stars like our Sun. They have surface temperatures between 3,900 and 5,300 Kelvin and contain about 60% to 90% of the Sun's mass. What makes orange dwarfs especially interesting is their incredible balance. They burn hydrogen more slowly than the Sun, allowing them to remain stable for 15 to 45 billion years, up to 4 times longer than our Sun's expected lifetime. Unlike many red dwarfs, orange dwarfs produce fewer powerful stellar flares, making them some of the best candidates for hosting potentially habitable planets. Because of this, astronomers often call them Goldilocks stars. Not too hot, not too cool, but just right for giving life plenty of time to evolve. One of the closest examples is Alpha Centauri b, located just over 4 light-years from Earth. Yellow dwarf star. A yellow dwarf, also known as a G-type main sequence star, is a medium-sized star like our Sun. Despite the name, yellow dwarfs actually appear white in space. They only look yellow from Earth because our atmosphere scatters blue light. Their surface temperatures range from about 5,300 to 6,000 Kelvin, and they produce energy by fusing hydrogen into helium in their cores. Yellow dwarfs are incredibly stable. They spend about 10 billion years on the main sequence, steadily providing heat and light. Our Sun formed around 4.6 billion years ago, meaning it's almost halfway through its lifetime and is expected to remain stable for another 5 billion years. Eventually, the hydrogen in the core runs out. The core begins to collapse while the outer layers expand, transforming the star into a red giant. Later, it sheds those outer layers and leaves behind a dense white dwarf. Every planet, Every ocean and every living thing in our solar system exists because of the steady energy produced by a single yellow dwarf, our sun. Blue giant star. A blue giant is a massive, extremely hot star that burns far brighter than our sun. With surface temperatures above 10,000 Kelvin, these stars appear brilliant blue because they emit much more high-energy light than cooler stars. They are typically 10 to 50 times more massive than the sun and can shine tens of thousands of times brighter. But that incredible brightness comes at a cost. Blue giants burn through their hydrogen fuel at an astonishing rate, so while our sun will live for about 10 billion years, a blue giant may survive for only a few million years. As their fuel begins to run out, blue giants continue to evolve into even larger and more extreme stars, such as blue supergiants or red supergiants, depending on their mass. Eventually, most end their lives in a powerful supernova explosion, leaving behind either a neutron star or, if they're massive enough, a black hole. In astronomy, the brightest stars are often the ones that live the shortest lives, and blue giants are a perfect example of that. Red giant star. A red giant is what happens when a sun-like star begins to run out of hydrogen fuel. As the core contracts under gravity, the outer layers expand dramatically, causing the star to become much larger and cooler. Red giants have surface temperatures between 3,000 and 5,000 Kelvin, giving them their distinctive red-orange color. Some can grow over 100 times larger than the sun. In about 5 billion years, our own sun will become a red giant. It will expand enough to engulf Mercury and Venus, and it may even reach Earth's orbit. Although the surface cools, the core becomes much hotter, allowing the star to fuse helium into heavier elements. Eventually, it sheds its outer layers into space, forming a planetary nebula while the remaining core becomes a white dwarf. Blue supergiant star. A blue supergiant is one of the most powerful stars in the universe. Unlike a blue giant, it has already exhausted the hydrogen in its core and entered the final stages of its life. These stars can be 10 to 100 times more massive than the sun and hundreds of thousands of times brighter. Their surface temperatures range from 10,000 to over 50,000 Kelvin, making them some of the hottest stars ever observed. Inside, they are no longer fusing just hydrogen. Instead, they fuse heavier elements, creating the building blocks for future planets and even life itself. Blue supergiants live for only a few million years before ending in a colossal supernova explosion. That explosion can briefly outshine an entire galaxy and leave behind either a neutron star or a black hole. One famous example is Rigel, the brilliant blue star that marks the foot of the constellation Orion. Red supergiant star. Red supergiants are the largest stars by volume in the known universe. They form when a massive star runs out of hydrogen in its core and expands to an enormous size. Some red supergiants grow to more than 1,000 times the radius of the sun. If Betelgeuse replaced our sun, its surface would stretch past the orbit of Mars and possibly even reach Jupiter. Despite their enormous size, they're surprisingly cool, with surface temperatures of only 3,000 to 4,500 Kelvin, giving them their deep red color. Red supergiants are unstable and nearing the end of their lives. They eventually explode as supernovae, scattering the elements that help create new stars and planets. One of the most famous red supergiants is Betelgeuse, located about 550 light-years from Earth in the constellation Orion. Hypergiant star. Hypergiants are the largest and most luminous stars in the universe. They're even bigger than supergiants, and are among the rarest stars ever discovered. Some hypergiants contain over 100 times the sun's mass and shine millions of times brighter. They burn through their fuel so rapidly that they survive for only a few million years. These stars are extremely unstable, constantly losing vast amounts of material into space. When they finally run out of fuel, they explode in one of the most powerful supernovae ever seen, leaving behind either a neutron star or a black hole. One famous example is Scuti, one of the largest known stars in the universe. If it replaced our sun, its surface would extend beyond the orbit of Jupiter. Rayet Star. Rayet stars are among the hottest and most extreme stars in the universe. They were once massive stars, but powerful stellar winds have stripped away their outer layers, exposing their incredibly hot cores. Their surface temperatures can exceed 200,000 Kelvin, making them far hotter than most other stars. They also lose material at an astonishing rate, ejecting vast clouds of gas into space every year. This is one of the final stages in the life of a massive star. One famous example is WR124, a Rayet star surrounded by a spectacular glowing nebula created from the material it has blown into space. White dwarf star. White dwarfs are not actually living stars. They are the leftover cores of sun-like stars that have exhausted their fuel and shed their outer layers. A white dwarf is about the size of Earth, yet it can contain up to the mass of the sun, making it one of the densest objects in the universe. A single teaspoon of white dwarf material would weigh around 5.5 tons on Earth. White dwarfs no longer produce energy through nuclear fusion. Instead, they slowly radiate their remaining heat into space, cooling over billions of years. Eventually, a white dwarf will cool completely and become a black dwarf. However, the universe is only about 13.8 billion years old, so no black dwarfs are believed to exist yet. Neutron Star. Neutron stars are the collapsed cores of massive stars that exploded as supernovae. They pack 1.4 to 2.1 times the mass of the Sun into a sphere only about 20 kilometers wide, making them some of the densest objects in the universe. A single teaspoon of neutron star material would weigh around 6 billion tons on Earth. They're made almost entirely of neutrons, created when gravity becomes so intense that electrons and protons are forced together. Many neutron stars spin at incredible speeds, with some rotating hundreds of times every second. Their surface gravity is about 2 billion times stronger than Earth's, so escaping their pull would be almost impossible. Pulsars. Pulsars are a type of neutron star that emit narrow beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space like the beam of a lighthouse. If Earth happens to lie in the path of one of these beams, we detect a regular pulse of radiation, which is how pulsars got their name. Some pulsars spin hundreds of times every second, and the most stable ones keep time with a precision that rivals atomic clocks. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell. The signal was so perfectly regular that it was briefly nicknamed LGM-1, short for Little Green Men, because researchers even considered the possibility that it was an artificial transmission from an alien civilization. Magnetars. Magnetars are a rare type of neutron star with the strongest magnetic fields ever discovered. Their magnetic fields are about 1,000 times stronger than those of ordinary neutron stars and up to a quadrillion times stronger than Earth's. If a magnetar were located halfway between Earth and the Moon, its magnetic field would be powerful enough to wipe the data from every credit card on Earth. In 2004, a magnetar called SGR 1806-20 released a giant flare that, in just 1/10 of a second, emitted more energy than the Sun produces in 100,000 years. Even though it was 50,000 light-years away, the burst was so powerful that it temporarily disturbed Earth's ionosphere. Black holes. Black holes are not technically stars, but they are formed from the remnants of the most massive ones. When a star with more than about 20 times the Sun's mass collapses at the end of its life, its gravity can become so strong that nothing, not even light, can escape. The boundary beyond which escape is impossible is called the event horizon. Beyond it lies the singularity, a point where matter is thought to be compressed to an infinite density, and our current understanding of physics breaks down. Stellar black holes typically contain 5 to several dozen times the Sun's mass, while supermassive black holes at the centers of galaxies can contain millions or even billions of solar masses. In 2019, astronomers captured the first ever image of a black hole, revealing the supermassive black hole at the center of the galaxy M87. Quark Star. Quark stars are hypothetical objects that may exist between neutron stars and black holes. In theory, if the pressure inside a neutron star becomes extreme enough, the neutrons themselves break apart into their fundamental quarks, creating an ultra-dense state of matter known as quark matter. A quark star would be smaller and denser than a neutron star, but not massive enough to collapse into a black hole. In 2002, observations from NASA's Chandra X-ray Observatory identified two unusual objects that appeared too small to be neutron stars and too large to be black holes, making them possible quark star candidates. However, no quark star has ever been confirmed, making them one of the most intriguing possibilities in modern astrophysics.